This is a summary for Chapter 9, Traversable Functors. I begin by giving a motivation, which comes from a computation where a list is processed by a function mapping each element to a future. It is natural to want to convert the result into a future of a list. I generalize the type signature to this one, which is a type signature of traverse. I'll give an example, traversing a triple, and how that could be implemented. And this motivates the questions such as, what other functors could have this operation? What other formulation we could have for traverse? What are the laws? And I explore these questions by first deriving a simpler operation from traverse. The simpler operation is sequence, which is a natural transformation with this type signature. I show traverse and sequence to be equivalent and give a type diagram. And I give some examples of traversable and non-traversable functors by using the sequence as the main tool for analysis. I show then that all polynomial functors are traversable in at least one way. I show what could be a freedom in defining the traverse. The freedom is in the order in which we traverse the elements of the container. I also show non-polynomial functors that cannot be traversable and indicate a paper that contains a rigorous proof of that. I then motivate laws for traverse operation. My motivation comes from category theory, which is I consider this type signature as a kind of lifting from one sort of functions into another sort of functions. And in category theory, all such liftings have identity law and composition law. And so I'm looking for the same pair of laws now. And I find them. I derive the corresponding laws mathematically. Then I derive the laws for sequence that follow from those. And the laws for sequence are simpler. There are three laws: identity, composition, and naturality. And I comment on the fact that naturality law is most likely going to hold by itself if we implement the natural transformation as generic code. But the other two laws need to be checked. I check these laws for constructions of traversable functors. I go through the detailed derivations for these four constructions, which are sufficient to build any polynomial functor, as well as any recursive polynomial functor. And I show that the identity law and the composition law hold for all these constructions if they hold for the previous functors such as g and h here. And also I briefly describe what it means to be a bifunctor and bitraversable. So in this construction 4, S must be a bitraversable bifunctor. And I show similar constructions for bitraversable bifunctors, which I do not prove because proofs are quite analogous, except for much more work dealing with all the type parameters. By restricting the applicative functor f to a monoid, I obtain a fold map operation out of traverse, which has this type signature, and I also show how to define the fold left method out of fold map. So it turns out, therefore, that traversable functors automatically have the methods fold map and fold left, which are usually understood as the methods of a foldable type class. And I comment on the necessity of having a foldable type class, which is basically a consequence of traversable, but it is convenient to have, if all you want is a fold, it's convenient to have a foldable type class. It's easier to define because the type signature is much easier. However, all foldable functors are traversable and all traversable are foldable, so it turns out to be the case. I then look at profunctors, contrafunctors that are traversed with respect to functors or vice versa. Since in the traversable construction we have two functors, one which is traversable and another functor which I denote by f everywhere, which is applicative. And the traversal is performed with respect to an arbitrary applicative f. Now, I explore what happens if we take a contrafunctor and want to make it traversable with respect to applicative functor f, or applicative contrafunctor f, or applicative profunctor f, and so on. And I find that all contrafunctors are traversable in a trivial way, and only in a trivial way. I also give a counterexample that profunctors cannot be traversable in any non-trivial way. And this will actually fail the identity law. So they cannot be, in general, traversable. And also, if we take a profunctor and want to traverse that, you find that the only way to traverse is to have the result ignore all effects. So the effects in the functor f must be ignored, which is probably not interesting for applications. So I give some examples of applications where you traverse a type constructor, which is a container, and you traverse with respect to some applicative functor or a monad. So the applicative functor and the monad supply an effect, and the traversable functor supplies data. So I show some examples with trees, and also I show how to use a state monad for traversal, and that allows us to implement scan left, and a function scan map that is equivalent, or that is similar to fold map. I also show an example of traversal of a tree that has a rigid shape. This is not a usual tree. It is not a monad, for example. It is an example of a recursive functor that is more general than what we have been considering in construction 4. And I briefly indicate what the construction could be for such more general type of recursive functors, but I do not give a proof for this, because probably it's rarely used, such constructions. I also give examples of what cannot be implemented as a traversal, say with a state monad. And the breadth first traversal and depth labeling, for various reasons, I believe cannot be implemented as a traversal with respect to a state monad. Maybe they can be implemented as some different kind of traversal, not the one we are considering here. After that, I talk about the concept of naturality that is generalized now to apply to a functor as parameter, whereas previously we had naturality with respect to a type parameter. Now we see an example that a traverse method is generic in the functor f. Not only it is generic in the type parameters a and b, but it's also generic in the applicative functor f. And I'll explain what that means, namely in what way we can mathematically formulate this and in what way we can intuitively understand it, which is that the code for traverse cannot use any information about the structure of f other than the function's pure zip and map. So I comment on category theory supplying a more general definition of lifting, where it is lifting not from functions on types, but lifting from a function on type constructors, which is a higher order type function, which is a natural transformation that preserves pure and zip, and maps them into pure and zip, and preserves the laws of the applicative. So that gives us a more general definition of category than what we have seen so far. Whereas before we only have seen morphisms indexed by type constructors, by ordinary types, and now we see morphisms that are indexed by type constructors. And finally, I give some exercises for this material.